Hello everyone, my name is Erik Derr. I'm a researcher at the Center for IT Security, Privacy and Accountability. And in today's talk I'm going to talk about the worrisome status quo of outdated libraries in the Android ecosystem. I will tell you why app developers don't update their dependencies. And finally, I will also announce a new Android Studio extension that will basically help you, the app developers, to keep your dependencies up to date. So let's get started. So third-party code is a double-edged sword. On the one hand, it eases software development, so you can reuse existing code rather than reinventing the wheel. This typically results in faster app development, reduced development costs, but on the other hand, it also increases the app's attack surface, because now you use code from different origins. If you are now additionally using closed-source components, you have to trust those third-party providers to adhere to security and privacy best practices. Now, Google recently updated its unwanted software policy, and presumably because of the GDPR data protection law. And as a result of this, you now have to be explicit in which user data you process and how you process it. And this does not only include the application code, but any third-party code that you include in your application. Now imagine you're using closed-source components, so how do you know how the library behaves? Well, let's give you some more numbers on the risk on using third-party code. So according to the central repository, more than 2 billion components with known vulnerabilities are downloaded each and every year. So of course it's not exclusive to Android, but Android of course has its fair share of it. Similarly, outdated libraries have a 3 times higher probability of being vulnerable as compared to up-to-date dependencies. And there's also the prominent OWASP top 10 list of security risks. And for the last 5 years, they include a risk entitled using components with known vulnerabilities, basically warn app developers about the emerging risk of insecure libraries. But these are only risk estimations, so what we actually want to know is, or what we actually want to do is, we want to quantify the security impact of third-party code on applications. And to do this, we have to do 3 things. So basically, first, we need to measure the status quo of outdated libraries in the ecosystem, such as Google Play. Second, we need to identify those applications that use library versions with known security vulnerabilities, with known privacy issues. And third, whenever there's a new application analysis coming out, then we want to make sure that we can attribute the results to the correct components, either the application code or some third-party code. And all those 3 tasks require that you have a reliable way of detecting libraries, even down to the specific versions in the application binary, so in the compiled APK. So how can we do this? And the challenges in detecting the libraries can be explained best by looking at how the libraries are integrated. So probably all of you are familiar with the developer view, where it starts. So for instance, in your Gradle file, you have a very explicit declaration, so you know which libraries you're using, which versions they're of, and typically you also know the source, so maybe Maven Central, JCenter, or some other central repository. But as soon as the app is compiled, this explicit mapping gets lost. So now any code, any third-party code is statically linked to the application code, and as a result, you receive 1 or more bytecode blobs. And further, we do not longer have different code origins. So now everything is merged into a single DEX bytecode file, and this has severe side effects, because now any third-party code is inheriting the permissions of the host app. So if the host app is able to access sensitive data like location, contacts, and so on, so does each and every included library. And past incidents have shown that in particular, advertisement libraries, tracking libraries, misuse these inherited access rights to stealthily exfiltrate personal user data. But we are not yet at the end of the story, because probably some of you also use ProGuard for obfuscation. Maybe not directly for obfuscation, maybe for optimizing the size of your APK, because you're adding more and more libraries. The size of the final APK keeps on growing, so you want to do something against this. One way to do so is using the built-in ProGuard. And what it does in the default config, it applies two things. So first, identifier renaming. So identifiers like the package name, class names, method names are transformed into short, non-meaningful character sequences. So for instance, Google would then be transformed into something like a.b. And further, that code elimination is applied. So typically, app developers don't make use of the entire library functionality. They only use a subset thereof. And as a consequence, ProGuard then strips any unused library code from the binary. And this poses some new challenges in the detection of the library, because now you must not only find the original library in the APK, but also subsets thereof. These subsets may change for each and every application. Further, we do not have to be only precise, but also scalable. Here we are talking about Play Store scale. So Play Store now hosting more than 3 million applications. And of course, you don't want to wait a year for the results. So how can we combine both precision and scalability? And we had the idea, okay, can we achieve this high accuracy by not even looking at the bytecode instructions at all, just looking at the code structure? So what do I mean by code structure? So assume you have some code. Now remove any bytecode instructions. So what is left is the function prototype. So the method name, argument type, list, and the return type. Now if we zoom out a bit, we further have the enclosing class and the package name. So the key insight here is Java, Kotlin code is organized in hierarchical namespaces, and these namespaces are preserved in the compiled X bytecode. So we can leverage that fact, pass those package names, and represent them as a package tree. So we can do this for the entire code of the application, and eventually we have a complete package tree that represents the code structure of the app. Of course, we cannot make use of those identifiers because they are all subject to identifier renaming. So we can only leverage the code structure for detection. So this package tree is not a suitable data representation for checking integrity. So we have to transform this package tree into a so-called Merkle tree. A Merkle tree is a hash tree where the parent nodes are generated by the values of the child nodes. Typically, they are used for efficient integrity checks for large data structures or file systems. And here we can use that package tree, transform it into a 3-layered Merkle tree, having dedicated layers for packages, classes, and methods. And of course, we can sort the hashes before building or generating the parent hash to retrieve a deterministic build order. So now the only question left is, how do we generate the method hashes if we do not have to look at the bytecode instructions? The only thing what is left is the method signature. So basically, package name, class method name, argument type, and return type. However, if we would simply hash the signature, then we would be again prone to identifier renaming, because any custom type can be renamed. So we have to tweak it a bit to make it resistant against that kind of obfuscation. And we can do so by simply applying a two-step approach. So first, we strip anything before the brackets, leaving only the argument type, list, and the return type. And next, we replace any custom types, or any non-Android framework type, with a common placeholder value x. So we are not interested in being able to distinguish different types. We just want to know how many custom types there are and what is their position. What we get is a so-called fuzzy descriptor. You can think of it as a pattern, a template. Now, the insight here is that we intentionally introduced an error at that point to defeat the obfuscation. Because obviously, this fuzzy descriptor would not only match the original signature, it would also match similar signatures. But as soon as we are building the tree, adding hundreds of methods, classes, and more packages, then we receive a very unique Merkle tree that represents a profile for our library version. Now, having such profiles, how can we leverage them to detect a specific library version in an app. The idea is pretty simple. First, we build a database of libraries. This can be automated to a large extent because more and more libraries are hosted and central repositories like Maven Central, JCenter, custom Maven repos. And then for each library version, we build such a Merkle tree. We do the same for each application that we want to test. And then we check for each library version. We take the package hashes and check if they are included in the application. That's simple. If they are in the application, we can already stop here because we have a full match, meaning that the complete library version is included in the application. In case of a partial match, we can go one level deeper in checking basically if the classes are included in the application. In that case, we would see 2 out of 3 classes and would then be able to report a partial match. For instance, the third class has been stripped by that code elimination. And additionally, we can also report the fraction of the original library code that is included in the application. So this was basically the approach that we use for detecting libraries. Now we want to apply it to the apps from Google Play. And first, we want to measure the outdatedness of the Facebook SDK, one of the more popular SDKs in app development. So on the left, you see more than 50 different versions spanning over more than 5 years, with the more recent versions on top. And now if we look at the results, you can see a very high fragmentation, meaning basically that each and every library version that is out there is actually in use. But the surprising thing is that these are not the results for all apps in the Google Play Store. These are just the results for the top 4,000 applications. And here you would typically expect that they have a proper code maintenance. And in fact, they have, but only for the application code, not for the included library code. And this gets problematic if you have a severe security issue like the one in version 3.15, where you could basically steal or hijack a victim's account. And as you can see, there's still in the most current versions of those apps, there's a significant or non-negligible number of apps using this very outdated version. But we were also interested in measuring how long does it take for app developers to patch such an issue. To that end, we took the 4,000 applications, we crawled the entire version history from Play, and then checked at which point in time this vulnerable SDK was introduced and which point in time it was actually fixed. So here you see a plot of a time span of about 2 years, starting with the release of the vulnerable SDK in June 2014. About 1 month later, Facebook released the patch. And naturally, within that 1 month time frame, there has been a number of apps or app updates that included this vulnerable SDK. But now with the patch, you would certainly expect that there's a steep decline in the number of apps that were affected. But the reality looks, unfortunately, a bit different. So there's even an increase, and even after a year, there are still apps and app updates, including this vulnerable SDK. And if you have a look at the fixing rate, you can see that there's only a small number of apps actually fixing the problem, either by updating to a non-vulnerable version or removing the Facebook SDK for good. Okay, so to recap this area, we've seen, due to our longitudinal study of dependencies, that over the years there has been a steady increase in the number of applications that are used by app developers. On average, there are about 13 libraries per application, or put it in other words, more than 70% of nowadays apps are from third-party sources, and only 30% is actually code written by the developer. With the increasing number of used libraries, we also have a steadily increasing number of outdated code. In our study, we found that over 70% of the libraries is severely outdated, so not just by a version or two, rather a year or two. And if the versions were updated at all, it took almost 1 year for the app developer to do so. Now the question is, why is that the case? So why do app developers not update their dependencies? What are the root causes for this? Of course, we have a lot of analysis tools, we have a lot of data, big data, so we could run some further measurements and do some educated guesses, but we wanted to find the truth, so we directly approached app developers. So we set up a survey, an online questionnaire, with a lot of questions that we had in mind, and reached out to developers from Google Play. And eventually about 200 developers did our complete survey. About 1/3 of them did Android developing apps as primary job. Pretty high coding experience, so 12 years in general, 4 years on Android, and an average of 13 apps that they already have worked on. So the questionnaire contained 28 questions that we grouped into 3 categories. Basically, we started, okay, what's the common workflow? Where do you search for libraries? How do you integrate them? Then we asked about the motivation and frequency of app and library updates. And finally, we directly asked them, okay, imagine your app contains outdated libraries. Why would that be? So in the following, I will guide you through the highlights of this survey, starting with where do you search for libraries? So any guesses about the top answer? Close. Top answer is the internet. So referring to search engines like Google, Bing, whatever you like. And only small numbers says GitHub and Stack Overflow. So thus indicating that there is, for whatever reason, there's no package manager for Android, like Cocoa Pods, Swift package manager for iOS, NPM for JavaScript, and so on. This was kind of surprising. And then ask, okay, what are the criteria to choose a library or to choose a library over another library? Of course, most of the people said functionality, it should actually do what I'm looking for. Open source and documentation are also quite popular answers. There are 5 more criteria, and the point where I'm getting to is security, because we are security researchers, and security and privacy was basically the answer from the least number of people. Asking about motivation and frequency of updates, we first asked, okay, what are the reasons to update an application? For sure, new functionality, bug fixes, but only 1/3 said, okay, we're doing app updates to update the dependencies. And then being asked about reasons to update the libraries included, almost any developer said bug fixing. Only a few said security fixing, and new functionality isn't relevant for most of them. And then being asked about reasons for outdated libraries, the top answer was the library was still working. So fair enough, never change a running system. The problem is, if you have security vulnerabilities, privacy leaks, they typically don't manifest in broken functionality. But still, everything works as expected, and still the end user is vulnerable, or the end user data is exfiltrated to some remote services. Then also unawareness of updates. Maybe this is due to the fact that there's no package manager, centralized package manager. But what we also find interesting is to prevent incompatibilities and too much effort. So that caught our interest. Because we wanted to know, okay, is it just a small number of app developers basically having this problem, or is this a general problem with updating dependencies? So we wanted to analyze that a bit further. So this actually boils down in expected versus actual update effort. What do I mean by this? So expected is which information drives app developers to assess compatibility of a new library version. And the actual update effort is basically doing the code analysis, checking how does the API evolve over time. So the expected update effort, we asked, okay, which information do you use to assess compatibility? So we asked about, do you read change logs? 86% said never or rarely. It was even worse for update documentation. Either they are missing in the first place, or they are read even less frequently. So still the question is, what information is always there and can be used as a predictor for compatibility? The answer is pretty simple. It's the library version string. Maybe some of you heard about semantic versioning. That's basically a 3-number versioning scheme. And it can be used as a simple compatibility indicator. So there's a set of rules that dictate how you have to specify the version string. So there's major, minor, and patch level. So you have to increase the patch level whenever you have code changes only, which are by definition compatible. You have to increase the minor version whenever you have backwards compatible changes. For instance, you add new functionality. And whenever you break existing API, so you rename API, you remove API, which can potentially break applications, then you have to change the major number. If you're not familiar with this concept, you should now read about this, because right after the Google I.O., Google announced that now, starting with version 15, the Place services and the Firebase SDK will now adhere to semantic versioning. All right, so this is about how app developers, how libraries developers specify the version string. But of course, their code changes have also to match that version string. So we wanted to find out if this is actually the case. And to do this, we have to check API compatibility across versions. The problem is, not always there is a specification, maybe you have an incomplete or missing API documentation, so it's just not scalable to check this for hundreds of different libraries programmatically. So the solution is we already have the complete library version history in form of the SDKs, the AAR files, so we can programmatically determine the documented public library interface. And here we have to consider that the public library interface by no means just the number of all public API methods. Because some of those public API methods are not intended to be used for app developers. For instance, if there are sub-packages named internal, like in the Facebook library. If you're using ProGuard to hide your internal code, then you have obfuscated class names, which can act as an indicator. So we follow ProGuard's renaming rules to filter those as well. And since we are working on the compiled Java bytecode, we also have to filter synthetic classes and methods, so basically everything that is compiler generated. When we do this, we get a very good approximation for the public library interface. And now we are ready to actually run the library release analysis. So basically, how do library developers specify the version string, and does this actually match the changes in the API? So we analyzed 89 libraries, for which we had at least 10 versions, totaling in about 2,000 versions. And here in the plot we see first the expected changes, so specified by the library developer. And this is really textbook, how you would expect this. So there's the vast majority of patch level changes, so code changes only, a few minor additions like new functionality, and some API breaking changes. But the reality is, of course, again, a bit different. So the vast majority is API breaking changes. And if we look at the library developers' misclassification by type, we see that from all misclassifications, about 39% are really problematic because the specified version string suggests compatibility, although there are API breaking changes. So next is updatability. So we've seen that there's a mismatch between specified version string and actual code changes, but you could still update without changing your code, even if it's a major, so an API breaking release, because it also depends on which APIs you're using in the application. So if the APIs that you are using are not affected, you can still update to the new version, even if it's a major update. So to predict library updatability, we have to check the API compatibility across versions, like we've seen it before. So here's an example, some Facebook APIs. We can map them to the versions in which they are supported. Next, we scan the text bytecode of the application for API invocations to that library. Then we can filter out any unused API, and then basically we can predict the highest version number that is compatible to the code of the library that you are using. We then applied this again to apps from Google Play. So we scanned more than 1.26 million apps. We identified more than 2 million library versions with a high accuracy. So everything where we are not exactly sure, we filtered out in this step. And the surprising example was JSON, so Google's JSON library, that had almost a perfect updatability to the latest version. So there are a couple of reasons for that. So there are not that many versions. Apps are only using a very small subset of APIs, so typically object from JSON and to JSON. And those APIs rarely change or almost never change across all library versions. But at the same time, we found 8 libraries with 0 to 20% updatability to the latest version. So basically, almost every new version of that library had some API breaking changes. So to summarize the results, we found 2 million instances. We filtered unused library code, for instance, due to code refactoring, developer forgot to remove it, and it was still packaged in the final APK. For those 1.7 million libraries, we found that over 1.5 million could in principle be upgraded without adapting the developer code. And even more than half of that could be upgraded to the latest version without, just by HOTS or just by replacing the version string. Okay, so we've seen that there are indeed a lot of problems. So how do we actually remedy this situation? I would argue that there's no silver bullet for this because it depends on different actors of the Android ecosystem. One is the library developer. The library developer does not adhere to semantic versioning, or the vast majority does not adhere to semantic versioning. Basically, this reinforces the fear of experiencing incompatibilities. Also, what we've seen, if there are severe bugs, security, privacy issues, there's no dedicated patch release or bug fix release. Often those releases are bundled with new functionality, and even existing functionality is changed or removed, and thus preventing easy adoption of those hot fixes. I think we additionally need platform support, so some central instance package manager where you can search for, where you can compare different libraries. Also development tools. I mean, currently we have lint. Lint does tell you that you have outdated libraries, but that's basically it. I will come to this in a second. And of course, the market operators, they could also improve by adopting state-of-the-art analysis to warn you once you're trying to publish your app if this app contains security and privacy issues that haven't been identified during the development process. So as said, typically I stop at this point, saying, okay, there's a lot of work to be done. This time not. So actually we did the first step. So we did create development tools. So basically we wanted to use our gained knowledge and the results of our analysis and put it in some Android Studio extension. I'm pretty happy that it worked out for DroidCon. So it was just approved by JetBrains 2 days ago. Basically the idea of up-to dependency is that it should facilitate the recurrent and tedious maintenance task of keeping your dependencies up to date. So it replaces the very simple lint checks for outdated libraries. And it basically uses our library API analysis results to do several things. So the first thing is that it additionally tells you what is the highest version that is compatible to the API that you're using. So basically, where you just can replace your version string with the new one, that's it. And if you want to update to the latest version that might be incompatible, it will tell you, or it will provide a complete report to estimate the update effort. Basically, it will tell you which APIs that you are using are no longer available And if we could infer alternative APIs from our analysis, it would also suggest, hey, look at this API, it's very likely that this is the replacement of the API that was removed. To give you a short glimpse on how it looks like, so this is pretty much similar to what the lint does right now in the Gradle file. It scans an outdated library. It says, okay, the latest version is 3.10, so please go for it. We can do a bit more. We can then say, okay, version 3.1 is the latest compatible version, so you shouldn't experience any problems. But what we also can do is, if you want to go for the latest version, and you click Show Me Dependencies, then what it actually does, it scans the code for API invocations to that library, and it will tell you which APIs are no longer available in the newest version. And in the last one, basically it's a constructor connection that takes a route, and we inferred that in the newest version, this constructor is no longer available, but an alternative that takes a route and an additional connection pool. So it's very likely that this is a replacement for this. What's the state of the prototype? The state of the extension. So like I said, we just got the first version done. It's the first prototype. We are constantly improving this, so we already have some features in mind that the results are already there. We just have to implement it in the IDE extension. First is we want to improve the updatability prediction with nested dependencies info. So for instance, if a library depends on other libraries that could affect updatability, we will also take this into account. Of course, since we are security researchers, we want to warn about the usage of insecure libraries, in the future also about libraries that do not adhere to privacy best practices. And of course, we have done this mainly for the community, so for the app developers. So we would highly appreciate any kind of feedback. So if you want to try that out, I will give you some pointers in a second. Then of course we would highly appreciate any feedback, so that if you can tell us what we can improve, this helps us, but in turn also helps you. So we recommend basically 2 ways on how you can give us feedback. But first things first, the extension works completely offline, so no worries about exfiltrating data. Everything is completely offline. It indeed does collect some telemetry data about how you used the plugin, whether our prediction was right or not, but you are the only person that can view the log. If you want to share it with us, you have to dump it to disk and send us an email with the log as an attachment. The second way on how you can give feedback is that in the next days we will put up an online survey. So basically a couple of questions, how you like the extension, what can be improved, what is already good. So if you want to help us, you can basically also do this online survey, but nothing of this is mandatory, so you can also just use the plugin. Okay, takeaways from this talk. So we've seen there were some status quo of outdated libraries in the Android ecosystem. So this is a long-term project where we wanted to raise the awareness for the fact that libraries are a really strong, really essential factor in app development, but it has two sides of a medal. All the analysis that you've seen so far, so detecting libraries, the API analysis of libraries, we built a tool that's open source. It's called LibScout. You can find it on GitHub, so you can play around, you can analyze libraries and so on. And then finally, as I said, there's no silver bullet to remedy the situation, so it really needs some combined effort. And we now took the first step in providing an IDE extension for the developers. You can find instructions how to get it, how to install it, and how to basically get in contact with us over project.cispa.io/up-to-dep. But of course, you also can come to me and my colleagues that implemented the plugin. Where are they? So here, we are around, so if you're interested, come to us, contact us. we would be happy to get some feedback. And with that, thanks for your attention.